observation about how we summarize the contributions of entropy to a system. And so here we're going to look at various factors. We're going to look at like temperature, particles, physical state, number of molecules versus number of atoms. And so let's look at our first one here, total entropy energy of a system. So if we have nitrogen at 10 degrees and nitrogen at 50 degrees, we think of if we increase temperature, how might that influence the overall number of microstates that we can have if we have more energy, right? We increase the temperature, we increase the average kinetic energy of all those molecules, and we can also think of increasing the total kinetic energy. And again, this is if we're thinking of a fixed amount of, in this case, nitrogen gas. Well, now we have more total energy. By having a higher temperature, we now have more energy in the system, which would mean there's going to be more arrangements or ways that energy can be distributed. And that's going to mean that's going to cause an increase in entropy as we increase temperature. And this has a direct correlation to this fact that when we increase temperature, we have a greater amount of kinetic energy. Because we have a greater amount of kinetic energy, there's more ways that kinetic energy be distributed, and so we're going to get a higher or increase in entropy. So that's looking at temperature. And that would be true if we're talking about a solid, if we're talking about a liquid, if we're talking about a gas, right? And if we're staying within that physical state, if we increase the temperature, we're always going to get to a greater amount of entropy. Now the next one that we want to look at is the number of particles in a system. So now if we have 1 mole of N2 versus 2 moles of N2. Well, now again, we're looking at the same molecule. And what we've done is we have more particles. We have more atoms. We have more molecules that we would see here. And if we increase the number of molecules or atoms or particles, in this case, we're thinking of the same thing of N2. Well, that would mean we're going to increase the number of ways or arrangements of energy in that system, because we've given it more energy, right? We have more particles, there's going to be more total amount of energy. We haven't changed the temperature, we haven't changed any bonds or anything. And because there's more ways that energy can be distributed, that's going to increase our entropy as well. So we just think of, we increase the amount of a substance, we can think of this as being, entropy is a physical property that is amount dependent, right? If I have 5 grams of water or 10 grams of water, the 10 grams of water, if they're both at the same temperature, is going to have a higher entropy just because we have more of that substance. Now the next one we want to think about is the physical state of the particles within a system. So let's say we have solid water, liquid water, and gaseous water. When we think of solid, we can think of these as stuck together in a rigid structure, right? So these water molecules are stuck together in a rigid structure. We think of water as a liquid. These are still stuck together, but they are fluid, right? These water molecules, that we can pour them, we can move them, they're fluid. In our gaseous state, these water molecules are not stuck together. So we don't have that limitation or restriction on their movement. They're not stuck together. Well, we'll see it in any gaseous state. They're very far apart. So there's basically no restrictions per se, except for maybe the volume of the container that they're in, that these water molecules would have. Well, we think, how is this going to limit the amount of arrangements the energy can be distributed for these different molecules? Well, if we're stuck in a really rigid structure, that means that we are going to have the fewest, and I'm going to use uppercase W, right, microstates, because there's the fewest ways that energy can be distributed because they can't rotate, right? They can't move around, they're stuck, they can vibrate maybe, but we have the fewest number of microstates. And then if we think of our gas all the way to the gas, what we'll see here is that it's going to have the greatest number of microstates, because they're so far apart from each other, there's really not that many restrictions. And then we can say this would have the middle amount of microstates, so W. Now we think, how is that going to contribute to entropy? And this has everything to do with the fact that they're stuck together versus they are stuck together and moving versus they are not stuck together and they're totally far apart in a gas. And so what we could say here is the entropy of a solid is going to be less than the entropy of a liquid. And I'm just going to go ahead and put a couple less than signs here is the entropy of a gas, because now we've gone from substances being stuck together to not. They're so far apart from each other. So a gas entropy is going to have so many more ways the energy can be distributed that it's going to have a much, much, much higher entropy than a liquid or a solid. And what we'll notice, if we're thinking of maybe something being dissolved, we can also say that the entropy of an aqueous ion is similar to the entropy of a liquid. When we're looking at maybe liquid water versus sodium chloride dissolved in that liquid water, right? So we have the ability to maybe connect those ideas there. Now, the last thing we want to look at is atoms in pure elements versus atoms in a compound. And so here we have N2, H2, and NH3. And we think, well, if we were to look at maybe a reaction here, where we were to make sure we had the same amount of each of these. So N2, let's go ahead and put our physical states here. They're all gaseous. And what we notice is that we have the same number of nitrogen atoms and hydrogen atoms in the 1 mole of N2 and 3 moles of H2 and the 2 moles of NH3. So again, if we look at our molar amounts, we have the same number of N2 and H2 versus NH3. And so because of this, it's not because we have more atoms per se that's going to cause us to have a difference in entropy. But what we notice here is that we have more atoms in that molecule, and that is going to be restricted in those covalent bonds. Versus our N2 and H2, these atoms they're smaller molecules. And because they are smaller molecules, what we'll see here is that they have fewer atoms in each of those molecules. Now, why is this important? Well, this helps us see is maybe this idea of how we thought about water as a solid, liquid, and a gas. If we have more atoms restricted in these covalent bonds, there's going to be less ways the entropy can be, or the energy can be distributed, fewer microstates. And we'll see here we're going to have more microstates. And that has everything to do with the fact that when we're looking at this, we can think about the fact that they are restricted in these covalent bonds. They don't have as much freedom to move around and distribute the energy. Whereas these individual molecules, where we just have N2 and H2, there's more freedom for them to be able to be distributed within that system. And so that would mean that we would have a higher entropy and a lower entropy when we're thinking about this idea of the same number of atoms, but they're maybe in smaller molecules versus larger molecules. So now we have these broad generalizations of how we can discuss entropy. And now what we want to do is we want to go ahead and take an opportunity to apply this to specific reactions. So what I'd like you to do is go ahead and look at reactions 1 through 5. And why don't you go ahead and predict whether you think the entropy is going to increase, so positive, when the reaction occurs, or decrease, negative, for our change when the reaction occurs. So we want to pay attention to what our reactants are, what our products are, maybe physical states, number of particles, etc. So why don't you go ahead and pause the video and then come back after you predicted the entropy change and look and see kind of how I thought through these. All right, so now you had an opportunity maybe to look at these and predict the sign. And when we're looking at these, it's one of the kind of more important ones that we think about when we have chemical reactions is we're going to focus on the number of particles or moles of reactants and products and the physical state of those. So let's go ahead and underneath each of these, let's indicate that. So here we have basically 1 mole of a solid and 2 moles of an aqueous molecule. And then we have over here, we have 3 moles of aqueous ions, and we have 2 moles of a liquid. So we can see here, there's 2 observations that we can make as we go from reactants to products. We increase the number of moles of particles total, and we go from, what we notice here is we have solid to liquid, and we still have aqueous and aqueous. So what we've done is we've gotten rid of these really low entropy molecules compared to these more high entropy molecules. And that what we see here is that we have kind of a conversion from a solid to a liquid. We still have aqueous ions. And so because of those 2 things, we're going to see an increase in entropy or a change in entropy that is positive. Now, as we're looking here, we also want to think about the idea of, well, what happens if they're backwards? And maybe we'll see that in a different observation. Reaction 2, again, we look at our reactants and products. So it looks like we got 1 mole of a liquid, 1 mole of a solid, 1 mole of a gaseous molecule, and then we have 2 moles of a solid. So again, as we go from reactants to products here, we have decreased the number of moles. And what we've done is we've gone from a liquid and a solid and a gas physical state to just a solid physical state. And so both of those is going to tell us that we have a decrease in entropy as this reaction occurs, or our entropy change is negative. And that is because those 2 contributions that we just talked about previously, the number of particles and the physical state. Reaction 3, we have solid carbon dioxide sublimating into gaseous carbon dioxide. And so here we get 1 mole of a solid to 1 mole of a gas. And as we go from reactants to products, basically what we're doing is we notice that in this, again, we're looking at our carbon dioxide from a solid to a gas. And we're in this, what we'll notice is that we have the same number of moles, but what we've done is we've gone from a solid to a gas. And we know that a gas has a higher entropy, and that's going to lead to an entropy of this reaction that is increasing, or a positive entropy change. Now we go ahead and we look at reaction 4. Reaction 4 is looking at lead nitrate. And this is dissolved in water, reacting with sodium chloride, which is dissolved in water. And I gave this one as kind of like a challenge for us to remind us about maybe double replacement reactions. And so we're going to get sodium nitrate and lead chloride. Lead chloride is insoluble. Sodium nitrate is soluble. Go ahead and balance this real quick. And what we notice is that we're going from 3 moles of aqueous substances to 2 moles of aqueous substances and 1 mole of a solid. So now we basically converted one of those moles of aqueous substances that we saw to a solid, and that's going to lead to a decrease in entropy, or an entropy change that is negative. Our last possible example that we're looking at here is 10 grams of nitrogen gas in a 20-liter container, and we're expanding it into a 10-liter container, we're expanding it into a 20-liter container. Well, now as that expands, what we've done is we've increased the volume available for our gaseous N2. It's the same amount of N2, but because we've increased the volume available, we're going to increase the number of ways those N2 molecules can occupy that volume. Right? We've expanded it. We allowed them to have more possible ways that they can occupy that volume. And what that means is we're going to see an increase in entropy as our N2 gas expands, or we could also say our entropy change would be positive. And this has everything to do with we're allowing the gas particles to expand into a larger volume. And because of that, they're going to have more ways, or microstates, the N2 molecules can occupy the volume, more way their energy can be distributed, and that's going to lead to an increase in entropy. Now, as we've looked at this, hopefully it gives us a good background in thinking about what entropy is, and then applying it to specific chemical reactions.